So we are going to continue the discussion we were having last week. We got to this point, right? We finished this closure example, did we not? I think we did. So a couple of things that we need to talk about. We are computing closure, and we have this algorithm for handling closure, which I don't know. Some people, I'm somebody that understands algorithms pretty easily. So I usually, I mean, if I read an algorithm, I pretty much understand it. But most people need, or a lot of people need examples. And we went through the example, but I don't know that you guys fully comprehend exactly what finding the closure of a set of attributes actually means. So whenever we get whenever we choose a couple or however many attributes it is that we're going to compute the closure for. So in this case, we chose AB to compute the closure, and I'm telling you, choosing AB is arbitrary. So it AB is there's nothing special about those attributes other than they're the ones that we want to compute the closure for. So you can choose any set of attributes from the relation to compute the closure, and the result will be the same. Not that the closure of every one of them is going to be the same, but what you find out by producing the closure is the same regardless of how many attributes you're computing the closure for or what those attributes are compared to the rest of the attributes inside of the relation. So we went through the process, blah, 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 computed the closure, and we decided that the closure of AB is A, B, C, D, E. So what that actually means is all of the functional dependencies that lend themselves from the one set AB are all of these. Remember, we talked about the combining and splitting rule. If we split out all the functional dependencies of the attributes AB, they would be AB functionally determined A, AB functionally determined B, so on and so forth all the way down, only you wouldn't include AB functionally determined A and AB functionally determined B because they are trivial functional dependencies, right? They're redundant. And so in reality, if I asked you to list all the functional dependencies that result from the closure of AB, you would list AB functionally determined C, AB functionally determined D, AB functionally determined E. And if I asked you to give me a list of all the functional dependencies inside of a relation, given the closure, then you would list all of the original functional dependencies, right? ABC, BC, AD. Actually, you'd list all of these that we listed here because we split them, plus the new ones that we just found from computing the closure. So does that make more sense on what exactly we're doing?
Yes, sir.
That's a good stock answer. I like it. Okay, well, if you don't, please let me know as we go through because this stuff is monumentally important whenever we get into normalizing relations. This is a big, giant portion of what you have to do in order to complete that normalization. So, anyway, all right, so um, let's go do another one. So I think this is the same set. So same relation. And the question is, does ABD follow from the set of functional dependencies, right? So AB functionally determining D, does that follow from the set of functional dependencies? And so we've already computed the closure of AB, A, B, C, D, E. And since D is contained inside of that closure set, then ABD does follow. So you can add that to the list of functional dependencies that we know about this particular relation. And that's the stuff that I just talked about. So now we're going to consider functional dependency D functionally determines A. So does this functional dependency follow from the list of functional dependencies that we have, right? So what's the answer to that? Can we say D functionally determines A from this closure set that we have determined from the closure of AB? So the real question is, do functional dependencies work both ways?
No.
No, they don't, right? So you can't say D functionally determines A since I've computed the closure of A, B, and D is contained inside of there. It doesn't work that way. And the way that you prove that is you compute the closure for D, right? So let's compute the closure for D really quick. So what is contained inside the closure set for D, given the functional dependency list? So you know D is inside of there. What else is inside the closure set of D?
E?
Yeah, I
E,
think it's
right?
just
So
D and
we
E.
are using the functional dependencies that we have, and the only one that we have that includes D is D functionally determines E, right? That's it. So the closure set for D is just DE, right? Adding E to the list of attributes in the closure does not help us. Remember, when we were doing this exercise and we were adding elements to it, so we added D to the closure set, D actually helped us because it added E, because we have this functional dependency, D functionally determines E, and so that allowed us to add E to the closure set. But as soon as we added E, there was nothing else, right? So E doesn't functionally determine anything inside of the relation, and so it doesn't add anything to the closure set. So because A isn't contained inside of the closure set for D, then DA does not follow. So there is no, D does not functionally determine A, ever. It just doesn't exist in this particular relation. And I mean, you got to think, like we're using A, B, C, D, and F inside of here as general terms, but in reality, these are going to be, you know, first name, last name, middle name, social security number, phone number, email address, something like that, right? And you're going to have to map out these functional dependencies with actual real world data inside of it, as opposed to generic data, A, B, C, D, E, F. So you guys okay with that?
Yes, sir.
So, okay.
Yes.
I'm going to give you guys a set of homework before we take an exam, and we're not going to take a test in this class for a while, probably, I don't know, mid to late next month, something like that, because we got to get through all of this stuff before we actually take it. And I'm actually thinking about, I don't know, splitting the normal exam that I give into 2 exams. I don't know. That might be a little bit easier on you. Maybe have an exam over just computing closure sets, and then have another exam where we're doing normalization and all that kind of stuff. I'll think about it and let you guys know as my brain decides exactly what I want you to do. All right, so let's move on. So the transitive rule. So we've already talked about the transitive rule in general when we were talking about inference. And the transitive rule is just the straight application of inference. So given a set, you know, A functionally determines B and B functionally determines C, it holds that A functionally determines C. And we went through the proof of why that is earlier, and you guys can go back at that if you want to. If some C's are contained inside of A, we may remove them from the right side because they're trivial dependencies. So that's just an application of that that inference that we did before. And we're going to use that constantly. I mean, obviously, we used it throughout the entire example that we just did here, right? So anytime that I'm computing the closure, I'm using the transitive rule. The transitive rule is what allows us to add elements to the closure set, because whatever attributes it is that we're computing the closure for, determines some other attribute, and that attribute determines some other attribute. That's why we can add it to the closure set as we're going through, because of the transitive rule. All right, so an example of the transitive rule would be if I've got title year functionally determines studio name, and studio name functionally determines studio address, then title year also determines studio address. And this is just, I mean, it's just going up the same stuff that we've gone over before. So now it starts getting a little bit hairy. So now we're going to talk about closures and keys, how to determine keys whenever you're determining the closure of attributes inside of tables. So we've got a set of attributes inside of a relation, and you know that a particular set is the key if and only if it is a super key of the relation. And again, we're going to go through an example of this so that you guys can see, and this will be something that you guys do over and over again. I'm going to give you examples where I'll say, here's a relation, here's all the attributes inside of the relation, and I want you to compute, or I want you to find the key of the relation given a set of functional dependencies. What that means is, right, if this is true, then that means that this set that we have functionally determines all other attributes, which is the definition of a key, right? So you can test this by computing the closure, and if the closure of that set of attributes is all of the attributes of the relation, then that set of attributes is a key for the relation, right? Does that make sense? Because the definition of a key is a set of attributes that functionally determine all attributes in the relation, in a single tuple of the relation, in a single row. So given a single row, these attributes functionally determine all of the other attributes. This is the primary key that we are creating inside a SQL server whenever we're creating our tables. So we need a primary key so that way we don't have redundant data inside of a given table inside of a database. So with that definition, the question I want to ask is, so given this, is AB a key for the relation that we're dealing with here? So the closure set is A, B, C, D, E, and the relation is A, B, C, D, E, F. So is AB a key of that relation? Cricket, cricket.
I'm gonna say no.
Why? Why though? Why is it not?
It doesn't include F.
That's right.
So
Right. So the definition of a key is a set of attributes that functionally determine all of the other attributes inside of the relation. So if AB were a key, then whenever we computed the closure of it, the closure set would include all of the attributes of the relation. So this is an algorithmic process by which you can determine the key 100%, right? You don't have to guess about it. You don't have to assume. You don't have to mushy squishy think about it. Although you do kind of have to mushy squishy think about the functional dependencies. So in a roundabout way, there is kind of a human aspect to determining the key. But if you have the set of functional dependencies and you're pretty sure that that is the finite set of functional dependencies that apply to the attributes inside of the relation, then you can compute the key without having to guess at it. And you don't have to get frustrated and create a new attribute, a new column inside of the relation that's like an ID that's whatever, some unique number that you're just generating, because you can't actually compute the key. You can go through the process of computing the closure for each one of the functional dependencies and determine whether or not any of them are a key. Does that make sense?
Yes.
Okay. Okay. It's a very definitive yes. I like it. Okay. Well, then we will move on.
Real quick. So, is there any way that you can use like some sort of reverse closure algorithm to determine the best key from a set?
So the best key, I wouldn't consider that a thing, right? It's either a key or it is not. And so in a practical manner, in the real implementation of a database, you are not, and I told you guys this before, you are not going to have multiple keys inside of a table. You will, you'll define a primary key, and that will be it. In theory, a table can have multiple keys, right? So you can think of the table that would hold your student information relating to your biographical data. So you're going to have your student ID number, right, which is a key, and you're also going to have some sort of other identifiable information like a social security number or something like that, right? So, and this doesn't apply to everyone. And so I guess technically it wouldn't be a key because we have foreign exchange students and stuff like that. But let's throw all that out and say we're just using people that have social security numbers, and we have student IDs. So student ID inside of that table is technically a key, and social security number, technically speaking, should be a key also. But in a practical manner, whenever you're setting it up inside of the database, you only choose one of those, right? And that one is probably going to be student ID number, because student ID number is used in all of the other tables inside of the database. And so you're going to choose student ID as the key for the relation because of that. Although social security number, technically speaking, could be another key, you're not going to choose. So in theory, if we were, just sitting down, theory crafting for the schema of the database, you would identify ID number and social security number as a key. But then when you went to implement that, you would choose one of those to use inside of the relation as opposed to multiple of them. So the best key, if you put those in quotes, that there is no best key. There's only keys or not keys, because the definition of a key says this functional dependency or these attributes inside of the relation functionally determine all of the other attributes. Regardless of how many there are, that's what it does. Given this set of attributes, they functionally determine all of the other ones. So there's no good or bad or medium or best or worst key. There's just keys or not keys. Does that make sense, Nicole?
Yeah, it does.
Okay,
Thanks.
good. Yeah, no problem. All right, so closure and keys, we talked about this, blah, 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 blah. Okay, yeah. So closing sets of functional dependencies. So given a set of functional dependencies, and they use S a lot for those sets, I guess, because S is the first letter inside a set. And I try to use the vernacular that the book uses inside of this as much as I possibly can. Any set of equivalent functional dependencies to S is said to be the basis for S. So a minimal basis for relation is a basis B that satisfies three conditions. And again, we're going to go through an example of all these, but I want to put the formal definitions out there for all of them. all the functional dependencies in B have singleton right sides, right? So this is the splitting rule. If any functional dependency is removed from B, the result is no longer a basis. In other words, if you remove a functional dependency, then you no longer have a key. If for any functional dependency B, we remove one or more attributes from the left side of that functional dependency, the result is no longer a basis, right? So it's just saying after you compute this stuff, you can't change any of it and it's still be a key. Otherwise, you just have redundancy in there anyway. So let's do an example. So we have a relation ABC. Each of the attributes functionally determines the other two attributes. So A functionally determines BC, B functionally determines AC, C functionally determines AB. So the set of derived functional dependencies are as follows. So full set, after we split everything up, and we're not done yet, right? So AA, BB, CC, AB, C, all of this stuff. You have to determine all of these given the rules that we have, right? So each attribute functionally determines all of the other. So you have to have the single functional dependencies for A, B, and C, and then you have to do the combined functional dependencies for each one of them. And our job here is to provide a minimal basis for the relation. So we're going to give a set of functional dependencies that are equivalent to the given list, right? So set of functional dependencies that are equivalent to this big, giant, long functional dependency list that we have inside of here. So A functionally determined B, B functionally determined C, and C functionally determining A. A, B, B, A, B, C, C, B. This set that we've computed inside of here, right? So the set that we just computed inside of here, these two sets that we've computed are equivalent sets to all of this stuff that we wrote inside of here, given the transitive rule that we learned before. So A functionally determined B, B functionally determined C, and C functionally determined A. From that, we understand that A functionally determines C. The thing that we didn't understand before, C functionally determining A, you have to list that. You have to list that literally whenever you're whenever you're doing a basis set for it, because the transitive rule doesn't work in a loop, right? So whenever we were computing the transitive rule before, A functionally determined B, B functionally determined C, so A functionally determines C. That didn't mean that C functionally determines A, right? We talked about that before. These functional dependencies don't work backwards. When we did that one example where we were saying, given the closure set, so back here in this example, when we computed this closure set, we were seeing whether or not from that closure set, you could say D functionally determines A because D was contained inside of this closure set, but then we computed the closure for D and determined that it does not follow, right? So the transitive rule does not work in reverse. So the basis for a given set of functional dependencies uses the transitive rule to shortcut the list of functional dependencies. Now, as a practical matter, when you guys, when I give you an exam or some homework or something, I'm not going to ask you to compute a basis for a set of functional dependencies, because technically speaking, I would rather you list the functional dependencies separately, because computing a basis for a set of functional dependencies is kind of like writing shorthand. If you guys don't know what shorthand is, so people who are like stenographers write in shorthand, which means that they use some symbolic representations for words or even phrases. And it's more difficult to interpret shorthand than it is if somebody was just to write something out. And so while I wanted to show you guys what a basis was, I don't necessarily like them. And so I'm not going to ask you to compute a basis ever. But given the rules that we have, mostly the transitive rule, you can compute a basis for a given set of functional dependencies that is way smaller than the functional dependencies themselves, as long as whoever's reading it understands that it is a basis and that you're using those rules in order to compute it. So that's all I'm going to say about computing a basis, and then we'll probably never talk about it again. But there it is. Projection, yes. So this one's actually going to take a while. So we're starting to get into relational algebra, and there's actually an entire chapter inside of the book about relational algebra, but I'm not going to get into a lot other than having to compute projection and a couple other ones that we have to compute. There are a set of symbolic representations for each one of the operations that have to occur, just like inside of normal arithmetic, there's a set of symbols, the plus sign, the minus sign, multiplication sign, division sign, all that kind of stuff. There are a set of similar things inside of relational algebra that you're not going to have to learn a ton of them. Obviously, projection, pi is used to denote projection. And we're going to have to talk about what projection is and how to compute it, but I can't do that in 6 minutes. And so I think we're going to stop there after we compute the basis, and we'll pick up on projection next time. So that's it for today. You guys got any questions before we go? You can stick around and ask. Otherwise, that's all I got for you today.
Thank you.
Well,
Have a good day.
Care for the
Yeah, you
next 2
guys
weeks.
too. I'll talk to you again on Wednesday, and hopefully things will be a little more together.
Yeah. Well, you take care now.
Yep. See ya.
See ya.